Chapter 7, Module 4. While discussing orbit spaces, we have said that the group that acts on a topological space has a strong connection with the fundamental group of the topological space, provided the space is a nice one. We shall formalize the term what we mean by nice topological space in this context and show that it really has a strong connection between the group that acts on the space and the fundamental group of the space. Let us recapitulate a few things. Suppose G is a topological group that acts on a topological space X, then the action defines an equivalence relation on the space X. As usual, this equivalence relation partitions the set into disjoint equivalence classes, and the equivalence classes are denoted by x bar for each x belonging to G. Now, these x bars are called orbits of the points of capital X. We collect all the orbits in a set x by G and define a map pi from x to x by G by x goes to the orbit of x. This x by G is topologized by means of the quotient topology induced by the function pi. X by G is called the orbit space of x under the action of the given group G. Earlier in this chapter, we have proved a theorem that a topological group G, when acts on a space X such that for every x belonging to capital X, there exists an open neighborhood V x with the property V x intersection G dot V x equal to empty for every G belonging to capital G with G not equal to identity element of G. Then the quotient map Q from x to x by G is a covering map. In view of this result, we have seen before that the quotient map Q from Sn to Rpn, the real projective space Rpn, is a covering map. Also, the quotient map Q from the cylinder -1 1 cross S1 to -1 1 cross S1 by Z2 given by the pair Sz goes to the class Sz, where the class Sz contains the points Sz and -S -Z is a covering map. This orbit space cylinder by Z2 is a Mobius band. Now, we define covering transformations. Suppose P is a covering map from x tilde to x, a self homeomorphism phi from x tilde to x tilde is called a covering transformation if the following diagram commutes. That means, if phi is a homeomorphism from x tilde to x tilde such that P composed phi is equal to P, then we call that function phi, the homeomorphism phi, a covering transformation. It is easy to see that identity map from x tilde to x tilde, which of course is a homeomorphism, is a covering transformation. If phi is a covering transformation, then as phi is a homeomorphism, phi inverse exists from x tilde to x tilde, and that is also a homeomorphism. It is easy to see that phi inverse is also a covering transformation. From this, it follows that the collection of all covering transformations of a covering projection P from x tilde to x forms a group under usual composition of mappings. The group of covering transformations of exponential map from R to S1 is the infinite cyclic group Z. Let us see how it happens. Consider the following diagram. We have the covering projections exponentials from R to S1. We take a function phi from R to R. We need to make that phi a covering transformation. So, the diagram commutes, and therefore, phi t will be n t for each n belonging to Z. Again, we need phi to be a homeomorphism. So, the collection of all covering transformations will be precisely the set phi n for n belonging to Z, where phi n is defined as the function from R to R given by phi n t is equal to n t for each n belonging to Z. Moreover, phi n is nothing but n times phi 1. That means, the collection phi n, which is forming a group as we have already observed before, is generated by a particular element phi 1, and therefore, it is an infinite cyclic group and hence isomorphic to the group of integers Z. In the next example, we see that the group of covering transformations of Q from Sn to Rpn is the finite cyclic group Z2 of order 2. We consider the diagram that Q is the covering map from Sn to Rpn and phi is a map from Sn to R. We need to get phi as a homeomorphism which makes this diagram commute. By commutativity of this diagram, we then have that Q composed phi of Z is equal to Qz. That means, phi of Z must be either Z or minus Z for each Z belonging to Sn. Since phi is a homeomorphism, phi cannot take some Z to Z and some to minus Z. So, the covering transformations are precisely phi 0 and phi 1, where phi 0 is the function which takes all the points of Sn to the same point, that means the identity function, and phi 1 Z is equal to minus Z for all Z belonging to Sn. Hence, the group of covering transformations is isomorphic to the group containing two elements, that is a finite cyclic group of order 2. Similarly, one may find that the group of covering transformations of P from R cross R to S1 cross S1 is the group Z cross Z. The group of covering transformations of the function P from -1 1 cross S1, the cylinder, to the Mobius band is the group Z2. Now we shall establish that if a topological space has a locally path connected, simply connected covering space, then its fundamental group is actually same as the group of its covering transformations. Before proving the theorem, let us recapitulate the definition of locally path connected topological space. A space X is said to be locally path connected at a point X belonging to capital X if for every neighborhood U of X there is a path connected neighborhood V of X contained in U. If capital X is locally path connected at every point of capital X, then the space is called a locally path connected space. This lemma can be established very easily. Let P be a covering projection from x tilde to x, and it is known that x tilde is a connected space, and let phi psi be two functions from x tilde to x tilde such that P compose phi is equal to P and P compose psi is equal to P. If it is known that phi of x 0 tilde is equal to psi of x 0 tilde for some x 0 tilde belonging to x tilde, then phi and psi will agree at every point of x tilde. In other words, if phi and psi are two continuous functions such that both the diagrams commute, that is P compose phi is equal to P and P compose psi is equal to P, and they agree at a single point x 0 tilde of x tilde, then the functions are actually equal. In particular, if we take covering transformations, then covering transformation is determined by its value at any point of x tilde. Now we prove the theorem that we were looking for. Let P be a function from x tilde to x, and it is known that the function is a covering map. It is also known that x tilde is a simply connected and locally path connected space. Then pi 1 x is the group of covering transformations of the function P. X tilde being simply connected, it is path connected. It is known that covering projection is a surjective map, so P is a surjection. Therefore, capital X is a path connected space, and hence pi 1 x is independent of the choice of the base point. Choose any point x 0 from capital X and x 0 tilde from x tilde such that the image of x 0 tilde under the map P is x 0. Let G be the group of covering transformations of P. For any phi belonging to G, we consider a path alpha phi. It is a path from I to capital X joining the points x 0 tilde and phi x 0 tilde. That means alpha phi 0 is x 0 tilde and alpha phi 1 is equal to phi x 0 tilde. Now, P compose phi is equal to P gives P compose phi evaluated at the point x 0 tilde is equal to P evaluated at x 0 tilde, and that is equal to x 0. Therefore, P composed alpha phi evaluated at the point 0 is P of x 0 tilde, and that is x 0. On the other hand, P composed alpha phi evaluated at the point 1 is P compose phi evaluated at x 0 tilde, and that is equal to the same point x 0. That is, P composed alpha phi is a closed loop in x based at x 0. Since it is a closed loop based at x 0, class P composed alpha phi will be a member of the fundamental group pi 1 x x 0. We define a map eta from G to pi 1 x x 0 by eta phi is equal to class P composed alpha phi. First, we show that eta is well defined. For if beta phi is another path that joins x 0 tilde with phi x 0 tilde, then by simply connectedness of x tilde, alpha phi is homotopic to beta phi. So, P composed alpha phi is homotopic to P composed beta phi, and consequently P composed alpha phi, the class of that is equal to P composed beta phi class, and that is happening inside pi 1 x x 0. In other words, if phi is any point of G, P composed alpha phi and P composed beta phi represent the same class within pi 1 x x 0, proving the function eta to be well defined. Now, we show that eta is a group homomorphism. Let phi and psi be two members of G. Then we choose a path alpha phi that joins x 0 tilde and phi x 0 tilde, and a path alpha psi which joins x 0 tilde and psi x 0 tilde. Then phi composed alpha psi is a path joining phi x 0 tilde and phi of psi x 0 tilde, and alpha phi of phi composed alpha psi is a path that joins x 0 tilde and phi composed psi of x 0 tilde. Therefore, eta evaluated at phi composed psi is equal to the class P composed alpha phi phi composed alpha psi, which is equal to class P composed alpha phi into class P composed phi composed alpha psi, and that is equal to the class P composed alpha phi into class P composed alpha psi, which equals to eta of phi into eta of psi. Now, to show that eta is injective, let us take 2 points phi and psi from G such that eta phi is equal to eta psi. We need to show that phi is equal to psi. Since eta phi is equal to eta psi, P composed alpha phi is path homotopic to P composed alpha psi. It implies that the lifts of alpha phi and alpha psi beginning at x 0 must end at the same point. So, phi of x 0 tilde is equal to psi of x 0 tilde. In view of the lemma that we have stated before, it follows that phi and psi are same. Now, to show that eta is surjective, so let us take class alpha from pi 1 x x 0. Let alpha tilde be the lift of alpha that begins at x 0 tilde, and suppose alpha tilde evaluated at 1 is y 0 tilde. Since capital X tilde is connected and locally path connected, and p sharp of pi 1 x tilde x 0 tilde is trivial, and that is contained in p sharp pi 1 x x 0, the lifting theorem says that there exists a continuous function phi from x tilde to x tilde such that phi of x 0 tilde is equal to y 0 tilde. We need to show that such phi is a homeomorphism. We observe that interchanging the role of x 0 tilde and y 0 tilde, we may get another continuous function psi from x tilde to x tilde such that psi of y 0 tilde is equal to x 0 tilde. Now, p compose psi compose phi is equal to p, and psi compose phi evaluated at x 0 tilde equal to x 0 tilde imply that psi composed phi is equal to identity of x tilde. Hence, phi is a homeomorphism, proving that phi is a member of G. That means, it is a covering transformation. Now, eta phi is indeed equal to p compose alpha tilde, that class, and that is equal to the class of alpha, showing that eta is a surjective function. This completes the proof of this theorem. Now, we see the power of this theorem in the following examples. Let us take the example of finding out the fundamental group of S1. We see applying the theorem that the fundamental group of S1 will be Z. How do we prove it? We just take the covering transformations of the exponential map from R to S1. Previously, we have seen that the covering transformations of exponential R to S1 is the group Z of integers. Now, the covering space R is simply connected as it is contractible, and it is locally path connected. Hence, by the theorem we get that pi 1 S1 is equal to Z. In the next example, we take RPN, the real projective space, when n is greater than or equal to 2. Earlier we have seen that the group of covering transformations of the covering map Q from Sn to Rpn is Z2, and Sn is a simply connected, locally path connected space for n greater than or equal to 2. So, with the help of this theorem, we see that pi 1 Rpn is equal to Z. If we take torus, then the fundamental group of torus is the direct sum of the infinite cyclic group Z with itself. We know that the covering space of a torus is R cross R, and the covering map is the exponential cross exponential, this map. Then from the commutativity of the diagram and applying the same technique, we get that the group of covering transformations of torus is Z direct sum Z. The fundamental group of a Mobius band is again Z2. That can be seen from the orbit space -1 1 cross S1 by Z2 of the action of Z2 on -1 1 cross S1, and the group of covering transformations of this particular orbit space is Z2, and we have seen that this orbit space actually represents the Mobius band. So, the fundamental group of a Mobius band is Z2. In this module, we have seen how efficiently we can compute the fundamental group of a topological space once we know the covering space of the given topological space. With this, we end chapter 7.